Welcome to the second webinar on HCB as part of the Spannovation educational series. And in case you tuned into the first one for the design, thanks for watching. And this is sort of a follow-up to that one. And I titled this, Use Your Imagination to Start a Fire, which is the story of HCB. So to start out with, what you see here is just a couple of the original sketches that went in with the first patent. And I want to give a brief history of like how the influence of patented bridge technologies over the literally centuries in North America, and then get into some of the constructability issues or constructability details inherent in the HCB, and then conclude with some things, some frequently asked questions, and hopefully kind of tie together everything you saw from the design video. So again, the beginnings of this really extend all the way back to about 1995, and the conception of the idea and the beginning calculations and specifications for a patent application. And you can see here the first patent was actually granted in 2000, about 20 years ago. And this is this in and of itself is a long, arduous process. But and it's not something we do a lot anymore, and I'll explain why. And some people might ask, why would you do this? And after going through it for a couple decades, and you realize how much work it is, obviously inventors want to benefit from the values of their intellectual properties. Some people refer to the HCB as the Hillman composite beam or the hybrid composite beam. I always found it kind of interesting that the first Hillman bridge, which looks remarkably like my technology, was an arch-shaped concrete bridge, and this was a system that was built back in Michigan, and literally 100 years ago. This is like 1922. I think there's about 40 of these bridges built, and again, you can see the arching effect of the concrete top of the beams. It's kind of like a pony truss type system. But so I think I like to throw this in just to demonstrate that there's nothing new under the sun. Again, flash forward 20 years, this is another one of the original patent sketches, kind of trying to break down the various components that are in the beam, and I'll go through that in a bit more detail. And this is just kind of a recap of what we had in the presentation. The whole thing was exacerbated really by discovering that there's this vacuum-assisted resin transfer molding process, VARTM for short. And you can see here how the beams are built. There's a shell on the left where they're laying up the glass, and then on the right you can see a completed shell with a flange getting ready to set on top of it. As we mentioned in the first one, the components we use a balanced quad weave fabric, so we've got sort of roughly the same weight of fabric in 4 different directions, which gives us longitudinal, transverse, and shear capacity. It's all infused in a vinyl ester or polyester matrix. The tension reinforcing is, again, just a 270 KSI galvanized steel pre-stressing strands embedded in the bottom of the beam, infused in and anchored at the ends. And then the compression reinforcing, again, is self-consolidated concrete, typically just a 41 MPa, 6,000 PSI. Self-consolidating so that it fills the beam, just flows in, doesn't require any sophisticated operations or pressure grouting, anything to fill the beams. And again, just to recap, what we end up with in the end is a structural member that's got several different building materials, using each one in its most effective properties, concrete and compression, steel and tension. The FRP box is serving as a stay-in-place form and gives us our shear capacity, and then we also make a composite with the concrete deck on top. But before there was an HCB, going back to the earliest advances in transportation, were just simply masonry arches and suspension bridges that were built for pedestrian bridges, basically for people to get from point A to point B. And then over the centuries, the patents had a huge influence on this. And hopefully there's some logic to this at the end. And Thomas Jefferson actually, and amongst all the amazing things he did, actually established the U.S. Patent and Trade Office back in 1790. And he was actually originally opposed to patents, thinking it gave the inventor an unfair monopoly. And then he later realized that there was a tremendous power in encouraging innovation, and that the inventor ought to be granted some protection or sort of a head start to actually capitalize on their intellectual properties, so that that there's some incentive to actually advance, and that's a benefit to our economy and the GDP and just the advancement of technology. And before there was Silicon Valley and smartphones and cyber world that we live in today, bridges were actually one of the most popular inventions of the day. And this goes back to, Theodore Burr actually was awarded one of the first patents in the U.S. back in 1817 for his wooden truss bridge that had an arch incorporated into it, which again looks remarkably like an HCB, just using different materials. Then there was a number of other really advanced thinking engineers with probably very little training and very few tools available to them, but they developed some pretty amazing technologies. Louis Wernbach built at one point, had a wooden truss bridge across the Schuylkill River in Pennsylvania that was over 300 feet long, which at the time, to build a 300-foot long truss out of wood was pretty amazing. Stephen Harriman was another great inventor. Again, similar technology you see here with an arch built into a wooden truss system. Long was also a pioneer. Then there was Ithiel Town that built these lattice work wooden trusses. People referred to these as the Town Bridge. And the covered bridges have always been sort of a fascinating part of American culture. And I note here that they call it covered bridge, the ethereal appearance of prefabricated metal trusses thrown across numerous streams, traditional arch and girder forms appearing in the garb of a new material, reinforced concrete. These altogether elicited more than 800 patents during the first century of the U.S. Patent Office. And I challenge you to find, even think that there could be 800 patents in some bridge technology in the next century. And if that wasn't enough, they invented the railroads, and along comes the Iron Horse. This is the Union Pacific Big Boy. And again, this transformed our nation, it transformed our economy, it transformed the world we lived in, much in the same way that aviation did, and then the telecommunications. Between 1871 and 1900, there were over 170,000 miles of track that were added to this nation's railroad system. And we were outpacing the rest of the world probably about 10 to 1. And a big part of that was the bridge. And that really fostered in again, a century of innovation. When most of you have seen these, the Pratt Truss, the Howe Truss, the Finks, the Warrens, the K Trusses, any number of innovative ways to span long distances. And keep in mind, all of these were patented technology. There are even more. There's the Burr's Arch, the Howe, the Childs, the Brown, and of course my favorite, the Triple Wipple, not to be confused with the single Wipple or the double Wipple. But again, it just everybody had some really clever ideas and tried to capitalize on it and find a better way to build bridges. And it's something we should probably still aspire to today. So you might ask yourself, where do I get a Triple Wipple? I doubt if you can find one anymore, but back in the day, you went to a Catalogue bridge company. So here, in this case, the Wrought Iron Bridge Company out of Canton, Ohio, actually manufactured a Triple Wipple. And there were many high-tech companies back in the 1800s. Again, this is before smartphone technology and computers, and some of the most sophisticated technological advances in the world were in bridges. Some of the more famous ones, the Phoenix Bridge Company, Keystone Bridge Company, which is actually Andrew Carnegie's first company, even prior to Carnegie Steel. And then probably was the King Bridge Company. And Zenith King, back in 1871, had established a company for basically, it's like the Sears Roebuck and of bridge technologies, and fabricated and constructed over 10,000 bridges. I've even seen some of these in some of the rural areas where the railroads service the farm communities, both in terms of getting the crops to market and delivering goods to people. And many of these bridges still last today. These catalog bridges, like this quote, appeared on the scene after the Civil War and became a ubiquitous feature on the American landscape. Arguably, they had more profound effect on the development of the American highway system than just famously landmark bridges by luminaries such as Raebling, Eads, Theodore Cooper, or James Finley. And this is true. I mean, we all gravitate towards the long span, sexy, complex, cable-supported bridges and arches. But the reality of it is, if you look at the U.S. bridge inventory, out of 600,000 bridges in our national bridge inventory, probably about 95% of them are less than a 100-foot span. Equally as important is just recognizing that nearly every paradigm shift in the evolution of our industry was a result of patented intellectual properties. And these included obviously the trusses and covered wooden bridges, the iron and steel trusses as they evolved with the catalog bridges, wire ropes for suspension cables, the spinning systems that were used to build those cables, those bridges. Almost every type of movable bridge. I lived in Chicago for 25 years. There's more movable bridges in Chicago than any other city in the world, and almost every one of them was a patented technology. The Schertzer rolling lift, the Chicago Bridge. Pre-stressing and post-tensioning systems were all patented systems. I mean, Eugene Freycinet was one of the pioneers. Even reinforced concrete itself was at one point a patented technology. And so, coming full circle, we get to this point, and again, I like to point out, what do these three objects have in common? Well, there's really two things. One is, if you look at the covered bridge over there up on the top left, that Theodore Burr's technology. Again, it was a basically a beam system or a through truss system that incorporated an arch, basically to carry the shear and make a stiffer, more efficient system. The photo below that is a cast iron railroad bridge in Tennessee back in 1860. And then the one on the right that you see there is actually the first proof of concept of an HCB. And again, you can see in terms of their structural form, they're almost identical, just different materials, but they're serving the same purpose and same fundamental load path. The other thing that they all have in common, and they're all patented technologies. So why did we stop doing this 100 years ago? Why did we stop advancing our industry and inventing new types of bridge structures? Well, ironically, there was this thing called Title 23 of the Code of Federal Regulations, subsection 635.411, that was passed into legislation in 1917 and was really only intended to be there for a year. And it was basically to counter the part of the breaking up the trust and counter the problem with corrupt patent officials and incompetent DOT officials that were exploiting the system. And it was an election year, no one was paying attention, and it just slipped through the cracks, and it stayed there for 102 years. And over that time, over that century, it became the _1 obstacle to innovation. And the reason is basically what it said was you could not use any federal funds to participate in, directly or indirectly, in the payment for any premium of royalty for a patented or proprietary material, specification, or process specifically set for the plans and specifications for a project. The only three caveats was you could use it if it was a demonstration project. You could use it if there was some sort of synchronicity in terms of you already have that type of bridge and you've got an HCB bridge and you want to widen the bridge so you can use those beams to widen it. But that's not going to happen unless you actually had the demonstration project. And then the last is if the technology was actually less expensive. And it seldom is in the first cost when you develop a new technology. It sometimes takes time for those economies of scale. But this was in place for 100 years, over 100 years, and it permeated our industry. We were basically set the trends for the world, and the whole concept of civil engineering and bridge engineering is like, you just don't patent anything. You just don't invent anything new. You know, there's no incentive for you to do it because there's actually a disincentive. You're spending all this blood, sweat, and tears and money to develop this, and you're not allowed to use it. But not to be deterred, after a long, hard, arduous battles with the Federal Highway Administration and basically Congress and a lot of support from folks like the American Road Transportation Builders Association, who were really champions in this cause, we were actually able to get this provision in the Code of Federal Regulation completely repealed. So again, let me reiterate, that provision no longer exists in the U.S. Code of Federal Regulation. So there is no constraint to use federal dollars for proprietary systems. So just something to think about if you're a young inventor and you got a crazy idea and you want to spend the next 20 years of your life beating your head against the wall to try to make the world a little better place. Again, I don't discourage you. It was a fabulous experience, and hopefully it's going to be a little bit easier now. It's still going to be hard. So as all that was taking place, and all the design methodologies were evolving, and the limit states and the testing and the materials sciences and all that stuff, again, it ultimately culminated in our first proof of concept bridge for an HCB in November of 2007 out in the desert of Colorado at the TTCI in Pueblo. And this was a 30-foot railroad bridge, Class 1 railroad bridge, 9.1 meters, designed for Cooper E80 locomotives, which is a pretty significant load. And the bridge performed quite well. This was the laboratory experiment funded by the High Speed Rail Idea Program. And we left it out there for a couple of years, ran it around the track, and everybody got comfortable with it. The photo you see there on the left is, I call it the $1 million photo. That's in the vein of the Latvian bridge engineering tradition, where the engineer has to stand underneath the bridge while it's being loaded. Fortunately, we'd already run the train for a couple of days, so we felt pretty comfortable nothing bad was going to happen. But still, a pretty rewarding experience. Not long after that, we actually had the first commercial installation of an HCB. And again, if you asked me 25 years ago, it's like, are you ever actually going to build a bridge out of this? That's kind of insane. I don't think that would ever happen. But it seems like it would work, and so we just kept plugging ahead and getting the grants, getting the patents, working through the design methodologies, actually building some smaller scale specimens in the laboratory, loading them to failure, scaling it up, and ultimately getting to the point where we actually built a bridge. And I want to point out this bridge has been in service for 12 years. Nothing has happened. If you look at it, it looks remarkably like a concrete bridge. It's very sleek. It's a six beams in the cross section. I believe it's about 42 feet wide, 57-foot span. The big difference is we put 6 beams on one truck. We set them with a 50-ton cherry picker. The contractor had a 150-ton crane scheduled. After he unloaded them with a forklift, he canceled that crane order and just decided to set them with his RTC. And you can see below too that underneath there's no intermediate diaphragms. There's cast-in-place concrete diaphragms at the ends of the bridge to transfer lateral loads, but for all intents and purposes, the HCB has enough torsional stiffness to be self-supporting without any lateral bracing during construction. So the biggest bridge we did to date, and that was really kind of, I think the third bridge that was constructed, was the Knickerbocker Bridge in Boothbay, Maine. And this is probably as good as any to really kind of point out some of the constructability aspects of the HCB. And this was an 8-span bridge. Typical spans were 70 feet long, end spans were 60 feet, for a total length of 540 feet, or 164 meters, which to my knowledge is still the longest composite bridge in the world. This one was also made continuous for live loads. So again, part of the inherent benefits of the HCB system, and this is why Maine DOT wanted to try it out. One is we were fabricating in their state, so they were excited about that, and they kind of wanted to push the envelope too and see, like, well, just how big of a bridge could we do with this technology? And again, an 8-span bridge is a great way to kick off your fledgling company. But the real benefit for them was that the bridge was being built adjacent to an old wooden trestle that was structurally deficient and functionally obsolete, and load rated to the point where if they had built this out of precast concrete boxes, which is what you would normally do, they couldn't even drive the trucks across the old bridge to unload them. They would have overloaded the bridge. So they would have had to build a steel trestle all the way across, basically build a bridge so they could build a bridge next to an old bridge. But you see here, I mean, we shipped 4 beams on a truck. Each one only weighed less than 3 tons for the picking weight. What the contractor was able to do is they already had a barge-mounted crane to go out and build their substructure, drive the piles and build the pile caps. Not a particularly large crane. They were able to use the same crane to offload all the beams. I think they were setting somewhere between, I believe they set about 2 spans a day. So they were setting about 16 beams a day. Once they got all the beams in place, they filled them with concrete, put basically the compression reinforcing in. You see on the right there just a tremie chute with a hopper up top, and they would fill that with concrete, and we have those holes about every 15 feet. That allows the concrete to flow out towards the ends, and when you see it come out the tops of the beams where the shear connectors are located, then you know it's full. So again, I think they were filling at least a span a day, 8 to 10 beams a day. And there's a lot to do. I mean, once you figure out the design limit states, there's a lot more to building a bridge than just satisfying the strength limit states and calculating the deflections. You have to work through all the little details. So in this case, like I said, we made this composite with the deck above, and we also made it continuous for live loads. So what you see on the right there is actually it's kind of referred to as like a Freycinet hinge. The idea is that there's some rebar that come out of the pile cap or the pier cap that cross over right at the base of the beam. So that allows for some rotation of the beams over the pier, the beams are sitting on neoprene bearings. And then you see some rebar extending through holes in the ends of the beams. And that's to cast, so we can have a cast in place concrete diaphragm, basically an extension of the pile cap up to the top of the deck. So that serves as our lateral load resisting system, but it also provides for continuity of the beams at the bottom, and then there's tension reinforcing on the top deck, which gives our continuity. Shot on the left, what you see is actually, again, we've got to deal with all the same details that you have in a normal bridge. So there was these are for cast in place diaphragms as well, and then there's the angle armor was cast in there for strip seal joints. As you know, we've got with a 540 foot long bridge, you've got to maintain some mechanism to accommodate the movement of the bridge from thermal loads. And in Boothbay, Maine, you see quite excessive thermal loads. But there's a number of other bridges we've done too where we just use integral abutments and just cast it right in, especially for the single spans. Other details that you have to consider in terms of, I mean, the idea is to make this look just like any other slab and girder bridge, so that the contractor doesn't need any special equipment. So there on the left, you see the rebar extending out for the shear connectors, but also posts to support the screed rails, so that when the contractor casts the deck, he can use just a conventional bidwell screed and come across the top and finish his deck off. Then on the right there, top right, you see scuppers that are cast into the deck. So again, everything's designed to accommodate all the conventional equipment that you'd use on any other type of bridge. Likewise, the bottom shot there shows you the overhang brackets. Anybody who's actually been on a bridge site knows that when you're going to have extend the cantilever deck out over the edges of the beams. and you also need a work platform when you're out there running your bid well. So again, everything's got to be designed to be compatible with, to the extent that it can, with conventional bridge construction technologies. So the overhang brackets are no different than you would see on a concrete or steel bridge. So again, some of the reasons to use an HCB, their lighter weight allows use of smaller equipment and a smaller pick radius, and possibly fewer cranes. The one on the left there you see is actually the second bridge we did in New Jersey, Route 23 bridge back in 2000. I think that was also 2008, and we substituted HCB planks for concrete planks, but they weighed 2,000 pounds a piece rather than 20,000 pounds a piece. Contractor was able to unload them with just a small excavator, 2 at a time. And this was a very congested site where they had overhead utilities on 3 different sides, shopping malls and both adjacent to the structure, an intersection just north of here, I mean literally at the end of the bridge. So the traffic staging was extremely complicated, and the fact that they were able to unload all those beams in about 3 hours made their life really great. The one on the right there you see is that was in Westbrook, Maine, and those are fairly substantial girders too. I want to say those were either 75 or 80 feet, and again, you've still got a fairly substantial crane out there, and these were actually pre-filled, but the idea being that you don't need to build a trestle. You don't have to get down in the river. You can easily set with a pretty conventional crane with a much larger pick radius. The other thing that this helps too is that without having to get down in the river or increase the temporary easements for construction, it can mitigate some right-of-way costs, building the causeways, complicating the environmental permits. Tides Mill Bridge was another kind of pushing the envelope with HCB. This is a project we did for Virginia DOT back in 2013. And what made this one really different was the fact that it was on a 45-degree skew. And so that was the big question: is like, can you build an HCB bridge on a very high skew? And the answer is it's actually a very good solution for a highly skewed bridge. Not a particularly long span. I mean, it's 44 feet. It's pretty much in the range of your conventional concrete box beams. But again, as I pointed out, that's about 95% of the bridge inventory in the U.S. For these, we used 21-inch deep HCB girders. We actually did an extensive amount of testing at Virginia Tech. They did an excellent job. Even built a 3-beam prototype in their laboratory, and fatigued it, tested it. The load frame wasn't quite strong enough to break the bridge, so we ended up splitting it into 3 different beams to do the final load test. And this was all done at the Thomas Murray Laboratory in Virginia Tech, where I did my graduate studies 30 years ago. So it was quite nostalgic. We've also done some marine structures, and this is one in Machias, Maine, which is again a 3-span continuous structure. It's still designed through the AASHTO codes using an HL93 truckload. But what makes this one really unique is it's a completely hybrid composite structure. The columns or the bent shafts there are actually concrete filled composite pipe piles that are driven down into the ocean floor. The cap is actually a 2-span HCB, where it's manufactured as a single unit, but actually has 2 arches built into it. There's a cast-in-place diaphragm between the HCB units, which helps to create the portal frame for the lateral loads in the overall system. And then the superstructure itself is also HCB double T's. So there are 2 beams with a single flange on top, made continuous for live load. And once again, this structure has been in service for 9 years. It's survived a Category 4 hurricane. It's survived some extremely brutal winters in up the northern parts of Maine. So again, very durable and resilient structures. One of the longer spans we actually did was the Dry Branch Bridge in West Virginia. And what made this one, also made this one unique, was the fact that it was actually built underneath I-64, just outside of Charleston. It presented some real challenges in terms of the erection of the beams themselves. As you can see here, the bridge is actually located directly underneath the existing I-64 bridge. And it's very challenging to get these beams in here. And one of the reasons the DOT selected this technology was the fact that they had a 105-foot span, and if they were doing this with concrete beams, it would easily be a 2-crane pick, because you'd have to offload it, get it across on a skid beam, have another crane on the inner side, and use the 2 cranes to pick it into its final location. In this case, the contractor was able to bring out a hydraulic boom crane. There's active electrical lines just parallel to the beam. You see there as they're picking it up. It's a very tight squeeze underneath the bridge, and they set them all from the abutment, and the contractor actually had to, the crane operator actually had to get permission from the owner of the crane to override the safety mechanisms, because it was such a tight spot. The crane itself would not allow you to snake that thing in there, but they set each one of these beams, each of the 3 beams, in 10 minutes. Again, 1 crane pick, and then cast the concrete arches after that. Put the deck on top, and I've got another photo. This bridge has actually been completely submerged in water. Seems like we get the 100-year storm every year now, but the beams are actually designed so that they're designed to accommodate the buoyancy of the uplift force, but they're also designed so that there's an access hole in the bottom that will lift up, allow the beam to fill with water, and then drain as the river subsides, so that we don't get any issues with the bridge floating away or getting stripped off the abutments from the stream flow load. We've experimented with a number of other different components too to make the bridges a little nicer. This is a bridge we did for the U.S. Army Corps at Fort Knox, Kentucky. Again, this is probably about 2013. And in this case, we actually used a pultruded stay-in-place deck form, safe plank from Strongwell, and we just inverted it. And so you can see from below, it's a very nice looking structure, because the beams were actually precast before they were set in place. I believe it was about a 60-foot span, designed for some pretty high military transport loads. And the safe plank actually serves as a stay-in-place form, and gives us a composite bridge all the way around. And this one also used steel diaphragms instead of the cast-in-place concrete diaphragms. So quite a few innovations with this particular structure. We've also done a couple of Class 1 railroad bridges, which is really fun stuff. And this is the first commercial application for Canadian Pacific. John Unsworth was a big proponent of getting us out there back in 2014 up in Fernie, British Columbia. And of course, the railroads basically invented accelerated bridge construction. And in this case, we pretty much had an 8-hour window from the time they shut off the last train. We had to go in, stage like a military operation. We had 1 crane on the north that pulled the old span out. They prepped the abutments. We rolled in with the new span from the south, set the girders, set the track panels, put the ballast, profiled the rails, and pretty much had the whole thing ready to go in about 6 hours. So it's amazing. The railroads are usually perceived as being pretty unsophisticated, but they've been doing this for over 100 years, and they're really good at it. So it was a lot of fun. Likewise, we did another bridge for BNSF out in the Boise City subdivision in Colorado. This was back in 2014. This is the longest railroad bridge we've done at 13 meters, which is roughly 42 feet. And again, 3 spans were replaced in 1 day. the HCB being only one of those, but again, everything was prefabbed, delivered, and ready to go. This is just a map you can find on our website that shows some of the installations we've done to date for highways, railroads, marine structures. Some of the other information you'll find there if you sat through the design seminar, regardless, in case you're wondering where to start. These are just some conventional sections that we have. The left shows sort of the highway bridge applications. The one on the right is for the longer spans where we've got a double cell box or kind of a U-girder that's also got a top flange. And those will push out to about 110, 120 feet. The conventional HCB that you see on the left is really cost effective up to about 75, maybe 80 feet. As they get deeper, it's a little easier to go to the double box. There's also some guidelines there for span ranges on railroad bridges in terms of the depth. Typically with the railroad bridges, span to depth ratios are going to be a little bit less, maybe 10 to 1, 12 to 1. And we usually manufacture these as just 2 units. So you see each unit's got 3 cells, usually prefabricated with the deck, the ballast curbs, and everything ready to set. So as I mentioned before, just some frequently asked questions, and usually when we do the design seminars, we get these, and so just kind of anticipating what people might want to know is that, how do we know if the HCB is properly filled? What if the strands are damaged in service? What happens if a truck hits the bridge? And how do you repair an HC bridge if for some reason it gets impacted? So we've had to deal with all these things over the course of the development commercialization. I like to refer to Missouri as known as the Show Me State, and we did three bridges there with Kiewit back on the Safe and Sound project. And they actually looked at a number of different technologies to validate that the things were properly filled. One was just using infrared thermography, which you see up top, and you can see with the heat hydration of the SEC concrete, it's pretty clear where the concrete is. Even prior to that, they actually built a mock-up with a mold and a plexiglass shield and a foam core so that they could visually see where the concrete went when they filled it. This is probably one of the more rewarding tests we did. Was again with the Virginia Tech Bridge. We had 3 beams in the skewed configuration, and again I wanted to point out with a skewed bridge, typically if it's steel, you have to have a lot of diaphragms to basically take the torsional loads as the load path wants to find its way across the shortest 2 points. With concrete, what you get is you get very stiff beams, and you'll usually have a topping slab. But in those cases, the bridge wants to, the wheel loads want to traverse across the bridge, or across the beams. So you get a lot of times you'll get reflective cracking in the deck. The HCB is sort of the best of both worlds because you get enough torsional rigidity in the boxes that you don't need any intermediate diaphragms. But at the same time, the bridge functions like a true skewed plate where you don't get any reflective cracking in the deck. It literally finds its way through the beams to the opposite corners. But like I said, we couldn't really fail the 3-beam configuration in the laboratory, so we split it into 3 beams. And one of the questions is, well, what happens if it gets damaged? So we went in and we cut 12 of the 22 strands that are in the bottom flange. We cut the webs completely out at mid-span, and we cheesed out all the foam. So at the end of the day, the only thing that was left of this beam at mid-span was the concrete slab up top and 10 strands down bottom. And there was an elaborate finite element model to figure out the nonlinear behavior of this composite structure and where it might fail. And I think the predicted load from Abacus was about 53,000 pounds. And when we got to 53,000 pounds, we had about half the deflection. In fact, it was still linear elastic. So the question was like, well, where's it going to break? And we took out all the sensitive equipment, and we just pulled the trigger. And I got out my HP 15C calculator on my iPhone and said, well, if it's a concrete beam, tension's equal to compression. And I know what the compression is in the concrete. I know what the moment arm is. So ideally, the strands or the steel ought to fail at 83,000 pounds. And that's exactly what happened. So again, these things are very predictable. they do behave like a reinforced concrete beam, and they're not that difficult to analyze and design. The other thing I mentioned too about that, I mean, again, keep in mind, it was 83,000 pounds on a single beam. An HS or HL93 truck weighs 72,000 pounds. And we had 2 lanes distributed over 8 beams. So we put over the equivalent of one HL93 truck on a single beam with half the strands cut out. All that being said, we've done quite a few laboratory tests on prototypes for various projects over the course of commercialization, and but the one thing the question we always get is like, well, what happens if a truck hits the side of a bridge? And there is no quantifiable load in any code that I'm aware of for lateral impact on a girder, but it happens quite frequently. So we donated one of the original railroad bridges to University of Tennessee. They set up they backed out a load. It came up with what they thought would be a severe case representative of a truck impact. So they had a 4.5-ton concrete mass and a steel casing going down a 30% incline and smashing into the side of the bridge with about 100 kilojoules of energy at impact. You can actually find this test on YouTube or on our website, and it bounced off. We did wreck the sled and the rails for the test apparatus, but the corner of the beam sustained some cosmetic damage, which again, this can all be repaired in place, and there was no damage to any of the steel strands, so basically no loss of capacity of the beam. This would happen to a concrete beam subjected to the same test. So again, probably not a fair apples to apples comparison, but still these materials are more brittle. So lastly, what happens if it does get damaged? And this was the CP Railroad Bridge got damaged. You can see the bottom; it scarfed out some fiberglass because it wasn't properly tied down on the flat car riding from Texas to Canada. So we sent our fabricator up there. They were able to just grind out the bad fiberglass. None of the strands were actually damaged or rusty. The rust you see there is just from the bolts, not the strands. Rebonded the laminates on bottom and reapplied the gel coat, and you basically couldn't tell that the beam had been damaged. So again, we use composite reinforcing systems and repair systems in concrete all the time. It actually works better with a composite beam where you're bonding composites to composites instead of composites to a concrete substrate that's still subject to deterioration. So that kind of wraps it up, but I want to circle back to the whole concept of intellectual properties and patented technologies and pushing the envelope with the evolution of our industry. And I'll start with a few examples here. This is the difference between Alexander Graham Bell's first concept of a telephone in 1876 and a smartphone in 2016. So that's 140 years of telecommunications evolution. And I don't need to tell anybody, how things have changed even during my lifetime. Same thing with aviation. I mean, the Wright brothers had the first controlled manned flight in 1903 at Kitty Hawk, and it just kind of evolved from there. And then if you look at the Boeing 787 Dreamliner, 106 years later, I mean, the difference in technology is just staggering. And then if we look at what's happened in our industry, here's a picture of a steel railroad bridge built in 1904 being replaced with a steel railroad bridge in 2014. So this is what 110 years of evolution of our industry looks like. And you got to kind of wonder why. Is it certainly the restrictions in Code of Federal Regulation using patented technologies and just the mindset of the engineer that we're not allowed to invent better things, compounded with the risk of actually putting something out there that's subjected to 2 million cycles of Cooper 80 locomotives every year. So it is a risky business. But if you're willing to use your mind creatively and come up with new ideas, it can be quite a rewarding experience. And there's going to be a lot of ups and downs, but getting back to the title slide, I always like this quote: "Success is not the result of spontaneous combustion. You must set yourself on fire," from Reggie Leach. That's me on the left at a high point. Again, one of the most prestigious honors I think I'll ever receive. And that's me on the right as president and CEO of HCB Bridge, having to do the dirty work, because that's just what you do when you're an inventor. Take the good with the bad. At the end of the day, it's all good. So that pretty much wraps it up. Again, I want to just emphasize, embrace your intellectual properties. Don't be afraid to push the envelope. Be careful, be safe, and please reach out to me if you got any questions. So thanks again to Raj Singh at Spanovation, and hope you enjoyed the presentation.